Okay, we're going to talk more about buffers. And before we move into the math a little bit, I want to review exactly how a buffer works because buffers are big in this chapter. And it's not that there's a lot of new math, it's just adding things in. Remember, a buffer is going to be one of two compositions. It's either going to be a weak acid and its salt, or it's going to be a weak base and its salt. Okay, and what the buffer does is it can withstand the changes. So for example, if you add an acid, which is either going to be hydronium or the hydrogen ion, it's going to act with whatever the negatively charged anion is going to be to form a weak acid in water, and neither of them are going to influence the pH of the substance, so they're just safer options. Same thing happens if you add hydroxide. There's going to be something to react with the hydroxide. A lot of times it's the weak base that's going to form the anion in water, that again, neither of them will influence pH. So it doesn't change as much, and that's what a buffer does. Okay, it keeps it within a safe range of things, so to speak. Now, the Henderson-Hasselbach equation is a shortcut where when you look at, here's the Ka version, this is what we've been doing, you can see that if you just manipulate it, it's just a rearranging of equations, okay? And so this can be our what's called our Henderson-Hasselbach equation, which is used when you know the concentration of both the base and the acid, and it's just a shortcut. So it's useful for calculating the pH of a solution when you know the concentrations of both the acid and the base and where the change in X is negligible. So you're using your 3 to 4 decimal places as your guideline on this, but if that is negligible, then you can use Henderson-Hasselbach. You don't have to use Henderson-Hasselbach. You can keep using what we've been doing, but for a certain acid-base pair, if they have the same ratio, they're going to have the same pH. So it's just another means to solve for these. So if you look at example on page 722, you want to find the pH of 0.75 molar lactic acid with the Ka value and 0.25 molar sodium lactate. Okay, so here's what you're really looking at in terms of what's in solution. Okay, you always got to take a step back and figure out, okay, what's there. And I've solved it two ways. The first one is regular old Ka expression. If we had an ice table, right, we can get rid of the x's, the 5% rule checks out. We get a pH of 3.38. Now this would be a perfect situation for us to use Henderson-Hasselbach. We can find the pKa value, okay, and then just plug the concentrations of our base and our acid right in, and we get the same answer. So it doesn't matter which one you use, because you're going to be able to get the same answer for both of them, regardless of the method that you take. So just another option. Now, 15.5, you have a buffered solution that contains ammonia. So in the last one, we had a buffer solution where you had the weak acid and its salt. Now we have another solution where we have the weak base and its salt. Okay, so it's just the other combination, and we want to calculate the pH of this solution. Again, you've got the concentration of both. You have the Kb, so we can do a plain old Kb problem. The only thing you want to keep in mind is that when you have weak bases, remember the chemistry that's going to take place is you're going to generate hydroxide. So you either need to use the POH equation first or Kw. You just need to make sure that you're not solving for hydrogen ion. So here's plain old Kb version, where you would our 5% rule would check out, and if you find POH, then you can subtract it from 14 and get the pH of 9.05 because this was our hydroxide concentration. You also could use Henderson-Hasselbach and plugged it in that way. You can use Henderson-Hasselbach using the Ka and Kb, but if you look on page 724, it's going to show you how to work that out just a little bit differently. So again, doesn't matter which one you use. All right, we also need to talk about what's called buffer capacity. Buffer capacity is how much it can withstand the change, and the amount of hydrogen or hydroxide the solution can absorb without a significant change in the pH. That's what buffer capacity is. Okay. It's determined by the size of the concentration of hydrogen of the weak acid and its base. And if the amounts are equal and they have large concentrations, it has the largest buffer capacity. And if you're trying to pick, the pKa of the weak acid should be very close to the pH desired for the buffer. Okay, remember, pKa is equal to pH. But that's what, we want those to be close. We've talked about some of those when we do half titrations and some of those lab scenarios. Okay, so this is just showing you buffering capacity. This is illustrating the fact that for letter A, you have large concentrations and they're equal to each other. So when you add in the 0.01 molar hydrogen ion, you get a very small change, okay? And that's what a good buffer does. It resists the change. Down in letter B, you have a different scenario. You're still adding hydrogen ion, but they're not equal to each other. And when they're not equal to each other, the buffer capacity is much lower, okay? Meaning that by adding the same amount, the pH changes by over 50%. So that's just a big shift on those. All right, and this again causes the change in pH after aciding acid to be much larger. So we want them to be equal, and we want them to be in high concentrations. Now I'm going to go ahead and refer you to the textbook on some of these to have you look at and look at some of the practice problems. There's 15.6 as well, which is on page 724. Then you've got 15.7 and 15.8, and what 15.6 and 15.6 walks you through when you add a strong acid to a buffer and the changes in pH that happen and when you kind of get to that tipping point. And then same thing, 15.7 is going to be the same type of problem, and it's just walking you through step by step how it changes. And then the other thing on 15.8, 15.8 is going to walk you through actually preparing a buffer. Okay, and some of your practice problems are all going to deal with this as well. But flip through these, and then we'll do lots of practice in class, and we will go from there. Okay, good luck.